Thanks also to the organizers for inviting me here. So I have to apologize. I have to use the slides because 10 days ago I hurt myself playing tennis. It's somehow a pity because it's very unusual to have these beautiful blackboards. So I want to talk about faithful actions of the Galois group. So I also have to apologize. I'm not a number theorist. I'm from complex geometry, so I will probably use completely different notation from the talk before, even if it's closely connected. And so what I talk about is a joint paper with Fabrizio Catanese and Fritz Grunewald. And this paper has a very long story. Actually, we were working with Fritz and studying certain type of algebraic surfaces, and we realized that we can make the Galois group act on connected components of moduli spaces. And we wrote this paper in 2007, 2008, and then unfortunately we realized that there was a very subtle mistake in it. And Fabrizio and I, we were very depressed, and it was Fritz who always said, no, I mean, the theorem is true, we can repair it, and we were just really working hard on this. But then unfortunately Fritz passed away in 2010, and we were really, I mean, we couldn't go on this paper, and eventually last year we saw how to repair the result, and for us it was completely unexpected how to repair it. So the Galois group, this is still a very mysterious object for me, even more that I'm not from arithmetic, and probably everybody in the room will understand it much better than I do. But the natural way is you make it act on geometric or combinatorial objects and try to understand it better by this. And another thing is, then it's interesting if you make it act on certain varieties, which geometric properties or invariants remain invariant under the Galois actions and which change. So more generally, if you take a field automorphism of the complex numbers, it acts on the space on the ring of polynomials. You just take a polynomial and you apply sigma to the coefficients, and you get another polynomial. And if you have a projective variety, so this is a subset of the complex projective space given by a finite number of polynomials, then you can sigma, you can apply it, you extend it coordinate-wise to Pn, and then it carries x to a set sigma of x, which is again an algebraic variety. And also if you have a morphism of projective varieties, so you can say its graph is a subscheme of the direct product and you get a conjugate morphism, but you can also really see it as conjugation by sigma from x to x sigma, and I will always call this at sigma. Now, you know that sigma is almost never continuous. Still, x sigma is a projective variety, and also f sigma is a morphism of algebraic varieties. Now, let me just say there are many, many results on faithful actions of the absolute Galois group, and I'm not quoting all, I could not. So there is starting Grothendieck's dessin d'enfant, and there have been also, so Grothendieck showed that it's faithful on dessins in genus 1. Then I think Laila Schneps in the 90s showed on descends of genus 0, and then I think Girondo and González-Díaz, they showed on every genus it's faithful. Then there is Easton and Vakil. Like 5 years ago, they proved that the absolute Galois group acts faithfully on irreducible components of the moduli space of surfaces of general type. And now there are many papers by González-Díaz, Jones, Torres, Teigl. There's also a newer one by González-Díaz and Heikin, for example, showing that there are arbitrarily large Galois orbits of certain surfaces, where I say a few words about it later. And there are many, many more. So that's on faithful actions. And then there is an old theorem of Serre from the 60s, which says that there is a sigma in the absolute Galois group, and there is a projective variety X defined over Q bar, such that sigma changes the fundamental group. Now, for me, the fundamental group is the topological fundamental group. What remains invariant is its profinite completion, the algebraic fundamental group. So these two groups, they have the same profinite completion. And let me put in the beginning a conjecture, which is really a generalization of Serre's result. So we conjecture that for each Galois automorphism, which is not the identity and which is not complex conjugation, there is a projective variety such that X and X sigma have different topological fundamental groups. So let me just give you in the beginning the main results, and I would like to explain you somehow the proof of these results. So the first theorem is, we claim that the Galois group acts faithfully on the set of connected components of the moduli space of surfaces of general type. So now you might say, why is this useful? Because, I mean, the Galois group is complicated. I can assure you the set of connected components of the moduli space of surfaces of general type is much, much more complicated. So I've been spending years on trying for certain surfaces to determine the connected components. That's really very, very hard. Usually we have no tools to distinguish connected components. So irreducible components, it's easier. So there's local deformation theory, but for the connected components, it's very hard in general. But we will make it actually act on a subset of the set of connected components, which are moduli spaces, which we can essentially reduce to the moduli space of curves. And then the connected components are determined as certain orbits of the braid group or the mapping glass group. So there it's much easier. And the second theorem is that for each Galois automorphism, of course different from the identity, and not in the conjugacy class of complex conjugation, there is a projective variety such that sigma changes the topological fundamental group. And the interesting thing is, I will show you the proof, and theorem B is a consequence of theorem A, which is not evident here from the beginning. So let me start to explain you this construction that we do. So we want to encode an algebraic number A in some geometric object, and we assume we have an A which is a complex number not in Q, and we fix an integer at least 3, and then we define what we call a very special hyperelliptic curve of genus G. So this is nothing else than I take a double covering of the projective line which is branched in this point A, and then I branch in minus 2g and in the numbers 0, 1 up to 2g minus 1. So I branch in something which is very asymmetric. I have this minus g on one side, and then I have all these consecutive numbers. And then it's an elementary lemma to say if I have two numbers not in Q, then CA is isomorphic to CB if and only if A is equal to B. So this is not surprising. So the proof is easy. You assume that CA is isomorphic to CB, and then there exists a projectivity, an automorphism of the projective line sending the branch locus to the branch locus. So BA is minus 2g 0, 1 up to 2g minus 1 and A, and this is sent to the branch B, branch locus BB. So in particular, phi has finite order, and it's easy to see that phi has to carry 3 rational numbers to 3 rational numbers, so it's in PGL2Q. And since A and B are both not in Q, and they're the only numbers not in Q, phi of A has to be B. And then we see that phi sends 3 consecutive integers to 3 consecutive integers, and this implies that it's a translation or minus z plus 2m. And this is, so the first one you see it has not finite order, and the second one you put in the numbers and you get immediately a contradiction. This can only happen for phi as the identity. Okay, so now we have this hyperelliptic curve CA, which is defined over Q bar, and we know by Bailey's theorem that a curve is defined over the algebraic numbers if and only if it admits a Bailey function. It admits a map to the projective line which ramifies in at most 3 points. So there are many Bailey functions, and you probably know that they're very, very difficult to control. So what we construct, or we use one known construction of a Bailey function, which is somehow, well, I call it functorial, so it doesn't depend on the 0 of the minimal polynomial. So I have fixed this algebraic number A, I take the minimal polynomial, and then I take the field L, and then I can write this curve, just Cx and replacing A by X. And then there is a rational function fx from C to P1L such that for each 0 of the polynomial, f alpha is a Bailey function. Okay, so we have now our curve CA and we have a Bailey function. But what I want to have is really a Galois covering. This Bailey function is not a Galois covering, it's not normal. So what I do is I take this Bailey function and then I take the normal closure of this curve CA, and then I have a group GA, which is a subgroup of the automorphism group of DA, which acts on DA, and the quotient is P1. It's a regular Bailey function, right? And then I have a subgroup HA, and it factorizes through my original Bailey function. Okay? So I have taken A, I've constructed CA, and now I have DA together with a GA action. Now this DA, it's a so-called triangle curve, which means it's a Galois covering branched in 3 points, which as a G covering is rigid. Right? There are no moduli of this G covering. Now, the problem that we have is the following. It boils down to exactly this. We can have that DA is isomorphic to DB, even as triangle curves, which means that DA has a G action, DB has a G action, and they are distinguished, so if I transport it with this isomorphism, they distinguish by an automorphism of G. I don't fix the embedding of G in the automorphism group. So what we have is that sigma, so if let's say B is sigma of A, so we constructed this Bailey function that sigma transports this subgroup HA. So dA modulo HA is just my curve CA, my hyperelliptic curve CA. It transports it, but if there is an isomorphism from dA to dB, then in general, F transports doesn't transport HA to AB because at F is not equal to at sigma, but there is an automorphism of G. Okay? So this does not imply that CA is isomorphic to CB. It does if we have an inner automorphism. Okay? So this is a rather crucial point because one could try, if I know GA, I know the automorphisms, right? And then I could try to repair. But there is no chance whatsoever because the degree of the Bailey function, this gets incredibly high and then we still have to take the normal closure. These groups are very complicated. They come up as wreath products. We have been doing a lot of experiments and they have a lot of outer automorphisms. There's no way to control anything. So what we do is we just overcome this problem by avoiding it, just fixing the G action. So we just go to marked varieties. Now what is a marked variety? So you fix a group, a finite group G, and a G marked variety. You can describe it as a triple. You have X, a variety. You have G, this finite group, and then you fix an injective homomorphism of G in the automorphism group of X. And you call two marked varieties isomorphic if there is an isomorphism F such that, why is this not working? Is it working? Yeah. Such that F transports this inclusion to the other one. Yes, but it's fixed. So there is no automorphism. We just, they are only called isomorphic marked varieties if the automorphism doesn't appear. Now you can define, of course, G-marked curves, G-marked triangle curves. I don't repeat all these definitions, but you fix the G action. And then the automorphism group of G acts on G-marked varieties. Yeah, you just compose this eta, this inclusion with the automorphism, changing, of course, the isomorphism class. And the remark is, if you do this with an inner automorphism, it does not change the automorphism group. Okay, so what we would have liked to prove is that the Galois group acts faithfully on the isomorphism classes of triangle curves. What we can prove is it acts faithfully on the isomorphism classes of marked triangle curves. So this is equivalent to say it acts faithfully on the regular descents. In fact, we prove more. We don't prove this abstract result. So we have our concrete to each algebraic number A. We associate this triangle curve D with the group GA. And we prove if dA is isomorphic to d sigma A as marked triangle curves, then A has to be equal to sigma A, which, yes, a subgroup of, yeah, group of automorphisms. Mm-hmm. Okay, so now we're still working with these triangle curves. Now I want to show you the the subset of the moduli space that we are considering. So we fix an integer g bigger or equal to 2, and we fix an algebraic number, and we suppose it's not in Q. And then we have constructed this curve dA with this action of GA. Then we fix another integer, g prime, and we consider all possible surjective homomorphisms from the fundamental group of a curve of genus g prime to my group GA. And these correspond to étale GA coverings from a Riemann surface C prime of genus G prime. Yeah, let's call this covering D, right? And now we have our group GA, which acts on DA, it acts on D prime, and then we can just make it diagonally act on D prime times dA and take the quotient. And since the group GA acts freely on D prime, it acts freely on dA times D prime, and we get that this surface, the surface is an étale quotient of dA times dA prime. Okay? Yes. Oh, I said dA times D prime. Sorry. Yeah, you're right. Okay. Now, such a surface, which is an étale quotient of a product of curves by a group, by a finite group G, so it's a Galois quotient, where I suppose that the genus of Ci is at least 2, it's called a surface isogynous to a higher product. I will just say isogynous to a product. And then let me just also say a G-marked surface. I will call it an étale-marked surface if the group G acts freely. So these surfaces here are equivalent to having S prime being a product of two curves, and C1 times C2 is an étale-marked surface. And S I call a Bouville surface if it's rigid. So rigid in the sense that it has no non-trivial deformation. The moduli space, which has as points the isomorphism class of surfaces, consists of a finite number of points. So this is equivalent to say it's a Bouville surface that G acts on C1 and it acts on C2, and Ci modulo G is the projective line, and it's branched in 3 points. So this is a Bouville surface. Now, I'm not talking about moduli spaces of surfaces of general type. You just have to believe me that there is a moduli space. It's a coarse moduli space, but the points of this quasi-projective variety correspond to surfaces, isomorphism classes of surfaces of general type. And in order to get a quasi-projective variety, you have to fix 2 numbers. So one I call chi, it's the Euler-Poincaré characteristic of S, and k squared, it's k is the canonical divisor. It's the divisor of regular 2 forms, and holomorphic 2 forms, and the self-intersection of these. Once you fix these 2 numbers, there is a quasi-projective variety parametrizing all isomorphism classes of surfaces of general type having exactly this invariance. And then I will just denote by M the union of all this MXY. And then I put xy bigger or equal to 1. We know that these invariants are integers. They're at least 1 if the surface is of general type. Canonical divisor. Canonical surfaces. Oh, I'm sorry. Well, you see, the point is the following. You embed these surfaces in some projective space with a pluricanonical map. And if you have minus 2 curves, you never get an embedding. They're always contracted to points. So I have to admit very mild singularities. And yes. Yes. But there is always a unique, minimal, a smooth model. So I mean, that's, yeah, that I mean by canonical surfaces. So, of course, we are talking, I told you, I can make the Galois group act faithfully only if I fix a G action. So I have to talk at least to mention that there is something like a moduli space of étale marked surfaces. And I denote this with het. This is the moduli space of étale marked surfaces S prime G eta such that if I divide S prime by G, then I end up in MXY. So this has S prime mod G has invariance chi equal to X and K squared equal to Y. And this is in general, if there is no surjective homomorphism from S prime mod G to G, this is empty. Otherwise, it's a finite étale covering of MXY with fiber just given the epimorphisms of the fundamental group. I always mean the topological fundamental group of X to G modulo inner automorphisms. So I have the moduli space, and I have, if I fix the G marking, then I get several different G markings, right? Right, exactly. That's it. Of course, if the fundamental group, if it's simply connected, there is no such moduli spaces, but in our case, we have very big fundamental groups. So the only thing you have to watch out that this S prime in our case will always be a product of two curves, right? And I'm interested in the surface, the quotients. So and now there is a theorem which makes life easier for these surfaces isogenous to a product. So the theorem says the following. Suppose you have a surface isogenous to a product, then any surface with the same topological Euler characteristic, the topological Euler characteristic is just the alternating sum of the Betti numbers, and the same fundamental group as S is diffeomorphic to S, and the corresponding subset of the moduli space, so corresponding to surfaces orientedly homeomorphic or diffeomorphic to S, is either irreducible and connected, or it is two irreducible connected components which are interchanged by complex conjugation. So let me formulate this. If I have any such surface isogenous to a product, so the isomorphism class is in some moduli space. So I know that all the surfaces which have the same topological Euler number and the same fundamental group, they can make at most 4 irreducible connected components. 4 because there is this orientedly. So what happens is I have, if I look at this, there are C1 times C2 mod G. I can take the complex conjugate of C1, I can take the complex conjugate of C2, and I have 4 possibilities. Of course, some of them can coincide. They can be isomorphic. Take G, the trivial group, then it's just 1. Okay? So in a certain sense, with these surfaces, the fundamental group determines almost everything. Right? There's topology, yes? So it's a quasi-projective variety, and I can decompose it in irreducible components. Now in this, so this is, forget this diffeomorphic. I don't look at diffeomorphism classes. I mean, I just say it's automatically diffeomorphic. Then I can look at on this C infinity manifold and can ask how many complex structures can it have? And if I have different complex structures, right? This is the moduli space of complex structures. Right? So this can be, I'm not claiming that I'm all, I mean, they're all diffeomorphic, but the moduli space, the complex structures, they can be different connected components. Right? So what is important I'm not want to enter in moduli theory. What is important is the moduli space of these surfaces, the Giesecker moduli space, which parameterizes all isomorphism classes as complex projective varieties. This consists of at most 4 connected components if I forget this in the middle, right? Okay? And irreducible means it's irreducible as a quasi-projective variety. Okay? And then I still have my algebraic number A. And then I just, by NA, I take the subset of all this moduli space, which is huge. It has infinitely many components, by all these S, which are given by dA times d prime mod G. All I get this, and they sit in some connected component, and I take all these connected components. Now, it's easy to see, it follows from the previous theorem, for each A in Q bar, NA is a union of irreducible connected components. Okay? And then if I make the Galois group act, then it maps the component NA, it maps to N sigma A. Okay? Okay, now the theorem is the following. It acts faithfully, the Galois group, on the set of connected components of the moduli space of Étale marked surfaces isogenous to a product. And how do you prove this? You take an algebraic number and then you consider the connected component. So I fix the marking. That's why I write het. And so I have constructed my dA and my d prime. I choosing this surjective homomorphism as I showed you some slides ago. And I assume that sigma leaves this component. It doesn't move this component. And then since I have this special construction, I get an isomorphism of marked surfaces. So dA sigma times C prime to sigma to dA times C2. And this is an isomorphism of marked surfaces. So if I had only the connected components of the moduli space, I could not say it's an isomorphism of marked surfaces. Now we know that the maps from the product of curves of genus at least 2, they are rigid, so this is essentially a product map. So F is of the form F1, F2, and since it's an isomorphism of marked surfaces, F1 is an isomorphism of marked triangle curves, and we have shown before that this implies A is equal to sigma A. Okay? Now, but this is not what I announced, so I mean we have to get rid of the marking somehow. So what happens if we forget the marking? Now, assume sigma acts as the identity on the connected components. So P0 is the set of connected components of this union of components which I have constructed starting from A. So the points of P0 are connected components NA mu, where mu is this surjective homomorphism. Always if I fix such a surjective homomorphism from the fundamental group, it gives me a G covering of curve C prime, and I get here a connected component. Now if I have a lambda in the automorphism group of G, then lambda changes the G action, and this corresponds, yeah, here it was n mu, and here it corresponds to n lambda mu. Now, you see, if I have S, if I look really in the construction, I have the isomorphism class of S here inside. Then S is of the form C1 times C2 modulo G. I just dropped the A, right, for the G. The group is fixed. And S lambda in NA lambda mu, it is given by the same product of curves, also divided by the group G, but the action is twisted by lambda on the second factor. Yeah? You have a question or? Oh, I'm sorry. Okay? So this G lambda, it's not the diagonal as we usually did. It's just G and twisted by lambda. Now, we know we have supposed that sigma acts as the identity. So it maps this component to this component. So my S lambda is isomorphic to some other S double prime lambda conjugate. And this is also in the same component. Okay? So this isomorphism lifts always to the product of curves. And if we identify here with these isomorphisms, then sigma, the Galois automorphism, acts on G times G by a product automorphism. So this times I did, before I identified my groups with sigma. And then F, the isomorphism, changed something, was only G equivariant, right? Here now I fix the isomorphism, and then sigma acts on G times G by a product automorphism, and it has to map G lambda to G lambda because the isomorphism descends here. And if you just work this out, you get that psi1 is equal to psi2, and lambda times psi1 is psi1 times lambda. So psi1 is in the center of the automorphism group, and since we before just were working out that inner automorphism don't change anything, we see that it's the class is in the it's in the outer automorphism group. Okay? So now I give you a hint of the proof of the first theorem, which says it acts faithfully on the connected components of the moduli spaces. So assume there is a kernel of this action. Okay? Now, this means for each A and for each mu, sigma in the kernel, I suppose that sigma is in the kernel, it stabilizes this connected component NA mu. And this means that we have a map, we have this sigma, and we get this automorphism of G, which is in the center of the outer automorphism group. And this is non-trivial if and only if sigma of A is equal to A, is different from A. Okay? So then one has to work a little bit. There is some technical detail that you show that sigma maps to psi is a homomorphism, a group homomorphism for fixed A and mu. Here we have to actually modify a little bit. We use that we work up to inner automorphisms, and we have to use, so we had a triangle curve, and we have to modify this triangle curve using that GA, this group, is the full automorphism group. But this is a technical detail, and it can be done. And then we can embed our kernel in this big product, but this is an abelian group. Right? It's the center, and then you take products. So we can show that this kernel is abelian. And then the theorem follows from a result of Fried and Jardin, which one can, actually this is not the theorem, this is a consequence. The only normal subgroup of the absolute Galois group, which is abelian, is the trivial group. So this proves the theorem. This is, what we actually would like to prove is that the Galois group acts faithfully on the isomorphism classes of Bouville surfaces. Why? Because Bouville surfaces, the moduli spaces consist of finitely many points. All the geometry of a Bouville surface I can completely encode in the algebra of a group. I can describe it group theoretically. I can calculate the orbits. I can just, if I have concrete situation, it's very easy with magma to calculate this moduli spaces, this point. So it's more a combinatorial object. So actually there is a recently Gonzalez, Diaz and Heiken, they announced that they can prove this, but it's not appeared, and I have not seen the proof. I don't know whether it's more explicit or, well. So, you see, what is, I was very surprised about this proof, because the difficulty is we cannot make this Galois group act faithfully on these connected components of moduli space. We cannot overcome these problems that we have to get rid of the marking explicitly, right? So it's a very, how to say, it's a very indirect proof. It's everything very explicit, but then we have to resort to some abstract result, which is rather unusual in the proof. You assume there is a kernel, and then you get a contradiction to, well, already that you can construct dysmorphism to an abelian group, it's quite surprising. Okay, but there is still theorem B. So theorem B is saying that if I fix a Galois automorphism, which is not conjugate to complex conjugation, then there is a projective variety X, such that X and X sigma, they have different topological fundamental groups. So you assume that there is such sigma. Now we know by an old result of Artin that the order of sigma has to be infinity. It cannot have finite order. And if I take the orbits of sigma on the subset of the connected components of the moduli space corresponding to these NAs, which were my surfaces isogynous to a product, they must have unbounded cardinality. So they have finite cardinality, but the number has to go to infinity. I don't need this full strength. I only want to have an orbit of cardinality bigger or equal to 5. So let's take this orbit of sigma. So S0, S1 is the conjugate of S0, S2 is the conjugate of S1, and so on, up to S4. And I know they belong to 5 different connected components. Okay? All these surfaces have the same topological Euler number because the absolute Galois group preserves the Betti numbers. If they had all the same fundamental group, then this is a contradiction to the theorem of Catanese, where the surfaces having same fundamental group and same Euler number, they can have only 4 connected components. But here I have 5. So there are at least 2 surfaces which have different fundamental group. Okay? So this is, it's very surprising somehow if you see these 2 theorems that one implies the other, but in fact it is like this. And actually there is another interesting result. By the same method you can see that there is no action of the absolute Galois group on the set of isomorphism types of groups, isomorphism classes of groups, which factors through the fundamental, associating the fundamental group, right? This can be proved also using this, essentially the argument that it has to, that each Galois automorphism which is not conjugate to complex conjugation and non-trivial has to have infinite order. Okay, thank you for your attention.